Hi level 3s, welcome back. This is 3.4 atomic structure and bonding, and we're on lesson 12, and this is part B. So this is the second part of the lesson, and we're now going to be doing calculations, and the type of calculation we're going to be covering today is using a calorimeter. Now a calorimeter is a really simple device that can be used to measure temperature changes, which we then plug into an equation, which is this one here, to work out how much energy has been released. So Q is actually energy, M is the mass of water, C is the specific heat capacity of water, and what that means is how much energy is required to heat 1 gram of water by 1 degree, and that's actually a constant, so it's 4.18, okay, and this is change in temperature. So the two types of calorimeters, which I'm going to talk you through now, are actually these pictures here. This is a terrible picture. You see some really daft stuff on the internet. Obviously, there would need to be a tripod there, or something to hold whatever you are heating, but there we go. So type 1 is this type here, which is an insulated container with a thermometer in it, and then you've got your water and then whatever you're adding to the water, so whatever solid you're going to add into here to have the reaction. So you can actually just use that. If we were in school, we would actually just use a polystyrene cup and have a lid on it. Okay, it can be as simple as that. So just an insulated container with a thermometer sticking in the top, must have a lid, and then your reaction takes place in here. So that's one type where you add, generally it's adding a solid to water. Okay. The second type is when you use a spirit burner, and again we would do this in the lab, and we will when we're back together. So inside the spirit burner you'd put some form of substance that's flammable, so something organic normally, so say we did ethanol. Okay, now you would weigh it at the beginning of the reaction. Okay, then in a beaker you'd put a set amount of water, okay, and have a thermometer, and so you would light your spirit burner, heat up a set amount of water, and when you'd finished the reaction you would reweigh your spirit burner, so then you could work out the mass of your liquid that had been burnt. So I hope that makes sense, but now I'm going to go through how the equation works now. But anyway, that's in essence what we're doing. So it's heat transferred to water, and we're measuring the change in temperature and relating that to an energy. Okay, so what do we need to know? We need to know the mass of the water in grams. Now some of you will be aware, I hope all of you, that 1 ml of water weighs 1 gram. Okay, now some of the questions lately have been talking about, in your exams, have been talking about mass of the final solution. So it's either mass of the water or the mass of the final solution. Okay, so bear that in mind, and I'll keep repeating that as we go through. Change in temperature is nice and easy, and I explained before what the specific heat capacity of water was. This is given in your assessment. You do not need to memorize it. It's the amount of energy needed to heat 1 gram of water by 1 degree. So this equation you need to know off by heart. Q equals mc times change in T. Okay, now Q gives you the unit joules. So most of the units that you will have seen before that we've been using when we've been doing enthalpy of combustion and formation and whatnot, they've all got the units kilojoules per mole. So to go from joules to kilojoules, you need to divide by 1,000, okay? And so you will have to do that because the units that you're required to use for NZQA are kilojoules per mole. Just what I've been saying, kilojoules per mole. Right, so a lot of the time in one of these calorimetry questions, they'll say to you, what is the enthalpy of reaction, or what is the enthalpy of combustion for this reaction? So that means that if you've just solved for Q, and Q's got the units joules, which you can then divide by 1,000 to make kilojoules, that's not actually in the unit of kilojoules per mole. So you actually have to do a final step to your calculations where to get kilojoules per mole, you divide by the number of moles. So you divide by N. Now this doesn't make much sense probably, or not complete sense until you've seen an example. So I'll come back to this, but you just need to know that you've got to read your question carefully and see if it's asking you to just calculate the energy. If it's just the energy, then you just do Q. And if it asks you for the enthalpy, then it needs to be you need to divide your Q by N to get kilojoules per mole. Okay, so here's type 1 that I was saying before, the insulated box, and you have to know the amount of reactants you put in. So you have to know the volume of water, and you need to know the mass of the solid you're adding, so e.g. 1 gram and 200 mils. Okay, the thermometer's there to record the initial and final temperatures, and sometimes there'll be a stirring stick, or sometimes we'll use a magnetic plate down here, and you can have a magnetic stirrer. You might have seen those, and that's just to ensure the heat's uniformly and it's all mixed and it's all uniform. So type 2 is that spirit burner, what we spoke about before, where you have a known volume of water and you weigh the spirit burner before and after. Okay, and you measure the temperature, obviously, before and after. Okay, so are calorimeters accurate? And the bottom line is no. Okay, and this slide's really important, so I want you to kind of make sure you're focusing right now. This can actually be worth a merit in your exam. Basically how the question will be phrased is, why does this experimental data not match the theoretical value published in textbooks? And there are there are 3 main reasons, and then this last reason is an extra one for the spirit burner. So let's go through these. So why might we not get the amount of energy we would expect being transferred to the water? And the first point is the most logical. Some heat will always be lost to the surroundings, and we can't avoid that. It's just going to happen. It's because heat transfer happens, okay? So we lose some heat to the surroundings, and therefore not all of the energy was transferred to the water. Now you'll see that I'm going to say a point and link it back to this, and thus not all the energy was transferred to the water. Because what kids do is they give a really good account. So they'll give one of these points really well and forget to link it to why the value's not correct. And it's because the heat energy wasn't transferred to the water. Okay, so some is always lost to the surroundings, therefore not all of the heat energy was transferred to the water. That's one reason, and that holds true every time. So if you learnt that, great idea. Okay, the second one, experiments in school laboratories are not conducted under standard conditions, because we can't always achieve standard conditions, okay, and therefore we wouldn't have the right energy being transferred to the water. Another one is that the apparatus might have absorbed some of the heat energy, so the glass of the beaker, if you were doing the spirit burner one, or the walls of the insulated container, and therefore not all of the heat energy was transferred to the water. Okay, the last one here is if you're doing the spirit burner type 1, incomplete combustion might have occurred. And if incomplete combustion occurs, not as much heat energy is being released in the first place, and therefore not all of the heat energy was transferred to the water. So, yeah, those are the main points. I recommend rote learning a couple of them. The first one's a very good one. And how could you reduce any of this? Use a more insulated type of equipment would be one. They'll always give you a question where it's pretty obvious, and it's always use insulated equipment. So you must link one of these points to this part in bold, that not all the heat energy was transferred to the water and therefore it's lower. Okay, I hope that makes sense. So here's an example calculation. So it says here, calculate the energy, so not enthalpy, just energy, required to boil. Water boils at 100 degrees. 650 grams of water that has an initial temperature of 23 degrees. So let's go through. We've got to know this equation off by heart. Q equals MC times change in T. The mass of water is 650 grams. Specific heat capacity is given. Change in temperature of the water. If water boils at 100 degrees, minus 23 is 77. Times them all together and your answer is in joules. Always Q is joules. Now that's a messy number, it's very big, so we're going to divide that by 1,000 to turn it into kilojoules, and we always at an NCA level 3 give answers to 3 significant figures, so 1, 2, 3 significant figures, and that is our answer. Okay, nice and easy. Now, example number 2, when 50 mils of water, mass, so that 50 mils equals 50 grams, which has an initial temperature of 23 degrees. 1 gram of sodium hydroxide is added and it increases to 26 degrees. Calculate the energy released. Was this reaction endothermic or exothermic? And how could we work it out for 7 grams? Okay, so the energy released. Q equals mc times change in T. Mass is the mass of the water, so 50 grams. Okay, 1 mil of water equals 1 gram, so 50 mils equals 50 grams. Specific heat capacity is that constant that you would be given, so 4.18, and change in temperature, which is going to be 3 degrees. So if we times those together, I actually don't know it off by heart, but you get a value in joules, okay? And then I'll show you the answer in just a second, but what is the reaction? Is it endothermic or exothermic? Now, if you see here, the temperature went from 23 to 26, which means the temperature has increased, which means when the reaction happened, heat was released into the surroundings, which means this reaction must have been exothermic. So therefore, that value should actually have a negative. Question 3, how could we work it out for 7 grams? Well, whatever this value was for 1 gram. So for 7 grams, it would be times by 7. Okay, so there was the answer, 627 joules, exothermic, and then times it by 7, so 4,390 joules, okay, and that actually could be transferred to, if we divided that by 1,000, you could make that 4.39 kilojoules, which would be much nicer. Okay, example 3. This is a spirit burner type example. So a simple calorimeter was used in the lab to determine the enthalpy of combustion of methanol. Write an equation for the combustion of methanol, and 2 grams was combusted in the spirit burner, resulting in an increase in temperature of 12 mils of water from 22 to 57. Calculate the heat of combustion. Heat of combustion is the same as enthalpy of combustion, which means you're calculating this. So not just Q this time. Okay, so let's start with our equation of combusting methanol. So we'll just jump over. So to combust methanol means to burn 1 mole in oxygen. So methanol plus oxygen, we always form CO2 and water, remembering the water is always in liquid state. 1 carbon, so 1 CO2 here. Okay, you then balance hydrogens. You've got 3 plus 1 makes 4 hydrogens, so we need 2 waters. We now need to balance the oxygens. You've got 2 O's, and 2 O's makes 4 O's, but you've got 1 O here, okay, and so therefore you're going to have to do 1.5 here. Hopefully that makes sense. The next step is to calculate Q. Okay, so Q, you use the mass of water. They said 12 mils, so that's 12 grams. Specific heat capacities are constant, and this is the difference in temperature. So the difference was 35. So when you work that out, you end up with 1,755.6 joules. If we divide that by 1,000, we get 1.7556 kilojoules. So that's kilojoules, that's the energy, but the question actually asked you for the enthalpy of combustion, which we know has the units kilojoules per mole. Now that's the same as saying kilojoules divided by mole. So all we're going to do is calculate our number of moles now. So they said 2 grams was burnt. So mass is 2 grams, and then we work out the molar mass. So carbon is 12, oxygen 16, and hydrogen's 1, and there were 4 of them. So if you add that up, you end up with 2832. So the molar mass is 32. So 2 divided by 32 is 0.0625 moles. So to work out the answer, we're going to take the energy and divide it by the number of moles. And you'll see that the answer here is negative 28.1 kilojoules per mole. Why have I put the negative? I've put the negative because it's an exothermic reaction. The temperature of this reaction went up. And therefore this has to have been a negative reaction because heat energy was being released. I'm going to pause here and we'll do a part C of this video.